Hello, Calc students. This is Mr. Beck. I want to welcome you to today's lesson. In 2.5, we're going to start by talking about implicit differentiation. Now, the idea behind implicit differentiation and why we care is our goal so far has been to figure out the derivative. The derivative will allow us to find the slope of the tangent at a certain point. Now, what happens if we have, say, a circle, which let's just say x squared plus y squared equals 25. How do we find the slope of the circle, or like a point on the circle at a certain point? Now, we can't really do this unless we turn it into a function, which it's a circle, so it's not a function. Because the circle is not a function, what do? Yeah, I know that there are ways that we could cheat this process. Mainly, y equals a plus or minus square root of 25 minus x squared. Definitely agree that that is an approach. We want to know whether it's the positive square root or the negative square root, and we could solve it that way. But what happens if we get something more complicated? X squared plus xy plus y squared plus 2x plus 2y plus 4 equals 0. Remember this from pre-calculus, we're talking about rotation of conics. First, we have to do x equals, et cetera, et cetera. Okay, do we really want to do that? No, we probably don't want to do that. We've got to find a way that we can figure out how to find the slope of a tangent line to not just any function, but any relation. So to do that, we're introducing this idea of implicit differentiation. Now, implicit differentiation, what do we mean when we say implicit versus explicit? So explicit is where we have a function of a single dependent variable, meaning, I guess that's supposed to be independent variable. But when we're talking about an explicit statement, all of the functions that we've been working with have been functions of x. Those are explicit. All of these relations are implicit because what we're doing is we're mixing the x's and y's together on one side. Sometimes we can write it as a function, sometimes we can't. For instance, xy equals 1, this first example that we have here, can we write this as a function? Absolutely. And so I'm going to solve this one explicitly. Y equals 1 over x, dy dx equals negative 1 over x squared. Pretty happy, right? Well, what about implicitly? Now, to look at this implicitly, we do not just have one variable as a function of another variable. In fact, one of the things I like to stress is this is more of a codependency. So codependency means that, okay, x and y, they do work in interaction with each other. For instance, if x equals 2, y is a half. And conversely, if y equals 2, x is a half. The two don't necessarily depend on each other, but they work together to come up with the overall solution. Now, when it comes to implicit differentiation, one of the things that we need to do is we need to look at our overarching function that's still here. This function is the product. So when I'm looking at this function as a product, when I want to take the derivative, I have to look at this as a product rule. Now, so far when I talked product rule, I always said like f prime g plus g f prime, f prime g plus f g prime. One of the ways that I think about it mentally is something that we refer to as differential notation. We're going to talk more about this in chapter 3, but anytime we have a product rule, I'm going to stress this as VDU plus UDV. It's no different from the product rule that we've talked about in the past, but it just flows off the tongue so much more efficiently, which means I'm going to use it as I'm talking. So with that said, we do have a product rule. So V, now du, the derivative of x is 1. But as we learned from the chain rule, that every function has a chain associated with this. The chain that we have associated with this is the differential of x. So this dx right here is called the differential of x. So again, every function has its own, or has a chain with it that is our differential of x. Now, whenever we took the derivative before, we said we're taking the derivative with respect to another variable. So this dx in the denominator is the respect that we're giving it. This is also the differential of x. So what ends up happening is this dx over dx ends up reducing to 1. So going back to what I was referring to before, we have v du plus u, then dv is going to be this entire expression. Now the derivative of y is 1, times the chain, which is the differential of y, and we're still doing the respect to x, hence the differential of x down here. So why did I stress it this way? Because a lot of times we're not necessarily going to find just derivatives with respect to x. Sometimes we might find derivatives with respect to y. Sometimes we find derivatives with respect to time, which is what we're going to do in the next lesson after today. So we're going to find derivatives of different variables with respect to time. We're going to work from there. So with that said, let's go ahead and simplify the result that we have. So we have y plus x dy dx equals 0, which leads us to say dy dx is negative y over x. Now, how is that equivalent to what we had in the past? Well, if we rewrote y as 1 over x, we can find that overall solution of negative 1 over x squared. Something that we should be pretty happy with and most students are comfortable with. So in example number 2, what I asked you to do is differentiate first with respect to x and then with respect to y so we could see exactly what's happening. So the derivative of x squared is 2x dx dx. The derivative of 4y squared is 8y dy dx. So dx dx does reduce to 1, and so we could just write it as 2x plus 8y dy dx equals 0. Now be careful, a lot of students don't remember to take the derivative of 4. The derivative of 4 is 0, so please just be on the watch out for that. So now simplify, dy dx is negative x over 4y. So we've been doing all these derivatives with respect to x. Let's do something different. Let's find the derivative with respect to y. So once again, derivative of x squared is 2x. The chain is dx. But now we're taking the derivative with respect to y, so that differential of y is in the denominator. And the derivative of 4y squared is 8y, chain of dy, now with respect to y, so that dy is in the denominator. This time the dy's reduce, excuse me, with each other. And since the dy is reduced with each other, then when we go to simplify our expression, 2x dx dy plus 8y is 0. And that looks a little messy. Let me go ahead and clean that up for you. Our derivative ends up being negative 4y over x. So this is the derivative of x with respect to y. Something that you should pay pretty close attention to is what is the relationship between these two. The relationship between these two is they are reciprocals of each other. And this is an important relationship because anytime we work with inverses, the derivatives of inverses are reciprocals of each other. And we can see it with the notation that we have here. For part B, if we take first our derivative with respect to x, we have v and then du plus u. And then this one is dv. Now keep in mind the derivative of cosine is negative sine. And then this dy dx is the chain of y. Simplified, we get dy dx is negative, or is 2 cosine x cosine y over 2 sine x sine y. And dy dx then ends up being cotangent x cotangent y. And I'm not sure why I don't have the other half of this on here, but if I took the derivative with respect to y, we should end up with dx dy equals the reciprocal, which is tangent x tangent y. And feel free to check that on your own. Example number 3. With example number 3, what we should notice is we have 2 distinct terms. And with these 2 distinct terms, we're going to end up with 2 product rules. So let's go ahead and set up some color coding here. So we have v, and then du is in blue. This is with respect to x, so it's dx dx. I didn't show it this time. Plus u, oops, that was supposed to be blue. Plus u, and then dv is going to be dy dx. And then we could do the same thing for the second expression, and color coding is taking too long. So v du plus u dv, and then the derivative of x, don't forget that the derivative of x is 1. So now we come up with a situation where what I'm looking at is I have this expression, And I have multiple dy dx's. If I have multiple dy dx's, what I need to do is go ahead, factor out the dy dx from two of the terms. And what you'll notice is I've brought this 3x squared y and this 2y over to the other side of the equation. And then that way I factor out the x cubed plus 2x. Really, I factor out the dy dx. And then when I divide, I get this expression. Now, something we need to note is that this problem says I want to find the derivative at x equals -1. So I don't know if you remember set notation, the set of all x such that x, et cetera, et cetera. This is saying that we're finding dy dx such that x equals -1. So if x equals -1, what I end up with, and I'm going to highlight this in yellow, I end up with this expression. Since I have that expression, I find this expression for my derivative still depends on y. If the expression depends on y, what I need to do is go back to the original equation and plug in my x value of -1 to figure out that y equals 1. And then I can go ahead and find the slope at x equals -1, or find the slope at the coordinate -1, 1. And I do have some highlighting that occurred there. I guess you can barely see it. All right, I did take this one step further and said, hey, what's the equation of the tangent line? The equation of the tangent line you see right here. We're using point slope form. Please, please, please use point slope form. For example, number 4, find the equation of the tangent line to this relation at that fractional coordinate. This is just going to be a little nastier work, but the thought process is pretty much the same. The derivative of x cubed is 3x squared dx dx. Derivative of y cubed is 3y squared dy dx. Then we got a product rule that we need to consider. So one of the things, you can subtract that overall product, or what I like to do is I like to say this is plus a -6. So then we have v. So v, and then du is -6 plus u. dv is dy dx equals 0. Derivative of 0 is still 0. Plug in our 4/3, plug in our 8/3, et cetera, and then simplify our overall result. And then we want the tangent line, so y minus y1 equals slope times x minus x1. Pretty straightforward. So let's move on. Now we get a little more complicated. Suddenly we have a power function. Within that power function, we have x plus y. So our derivative is going to be the derivative of the power. Let me go ahead and change colors. So what I'm looking at is this is my overarching function. So 3 times what's inside squared is the power rules derivative, how it changes. And then we do have the chain, meaning the derivative of what's inside, which is the 1 plus dy dx. Then derivative of y squared is 2y. Is 2y dy dx. Derivative of 5 is 0. Once again, we have multiple dy dx's. Since we have multiple dy dx's, what we're going to have to do first is we're going to have to distribute this whole expression to both the 1 and the dy dx, which is why I have 2 distinct terms here. And then, like before, we factor out the dy dx, which is what I did here. And then bring the other term to the other side, and then simplify, or divide to simplify. For part B, same thing as before. My overarching function is the sine function, so the derivative of sine is cosine. And then we have times the chain of what's inside. Chain of what's inside is going to be 2 plus 3 dy dx, as you can see here. Pretty straightforward. And then suddenly we're like, wait a second, I have multiple dy dx's. So just like before, I am going to have to distribute, I think I used green on this, I'm going to have to distribute this expression to both the 2 and the 3 dy dx. I also am bringing the 2 dy dx to the other side by subtracting. Once I get there, I factor out the dy dx, bring this to the other side to get this expression. And I'm happy with this expression. But oftentimes in the back of the book, they're not going to have this expression, they're going to have this expression. And it's your job to say, how do we get from one to the other? And the answer is we factor a negative out of both the top and the bottom to get to that result. So I'm happy with either one of those answers. Multiple choice, just be sure to choose the correct one. For your response, I would accept either. And then part C, logarithms. What we've learned from logarithms is logarithms are very, very flexible if you know how to use them. And thankfully, we do know how to use these. So I'm going to take the natural log of the square root of xy and break it up into 1/2 natural log of x plus 1/2 natural log of y. Once I have that, this is just really a straightforward rewriting. Suddenly now I can take the derivative, and the reason why I want to break this apart is because my derivatives are very, very nice. So remember natural log's derivative, 1 over what's inside times the chain of what's inside. That's how we get 1 over x times dx dx. And then in derivative of natural log of y, 1 over y times the chain, which is dy dx. And then straightforward derivatives here. Now I have dy dx on the right, I have dy dx on the left. We're going to bring that dy dx over to the right, factor it out, and then then divide. Now, once we get to this expression, this is something we cannot leave. Anytime we have a fraction within a fraction, we multiply by the LCD over itself to get this expression, and then from this expression, we can factor out the y from the numerator, factor out the x from the denominator, and we have this overall result. We're experiencing just a little bit of a lag. So I apologize. Now, implicitly finding the second derivative. I don't know if any of you have noticed this d squared y over dx squared. Why is the second derivative written that way? It's because we're really taking the derivative of the function or the relation y with respect to x twice. So that's one way to approach it, but you'll see this d squared y over dx cubed. You'd see it as d cubed y over dx cubed. So when we're finding dy dx, or the second derivative, we have to begin by finding the first derivative. Pretty darn straightforward, so there's nothing that we need to say about that. Now, when we solve for dy dx, we get x over y. And then to take the second derivative, we have a quotient rule. So our quotient rule is going to say v du minus u dv over v squared. And then we say, what are we doing with that? And what we're doing with that is we are going to then substitute. Let me change colors on this. Let's make it purple. If this is dy dx, we're going to put it in place of dy dx here, which is the x over y. And then once again, we have fraction within a fraction. Since we have fraction within a fraction, we go ahead and reduce. And I am comfortable with that expression unless we see that, okay, wait a second, there's got to be some relationship to the original problem. And that's where we have this as our overall solution, that we know that y squared minus x squared is equivalent to -8. And that gets placed in down there. Now, why is this important? Because the second derivative shows that it's dependent upon the first derivative and dependent upon the original relation. So it's important to be able to look back and say, is there a way that we could simplify this overall expression to make life easier on ourselves? For part B, we could do the exact same thing. First derivative, 2y dy dx equals 3x squared. Solve for dy dx, and then we now have a quotient rule. So quotient rule is v du minus u dv over v squared. And then once again, substitute dy dx in here. Once we substitute that in, multiply, or I guess I simplified here first, but then multiply by the LCD, y over y, to get this expression. And then going back to the original beginning, we know that y squared equals x cubed. So if we replace y squared with x cubed, we now get an expression which looks like this. Now the question is, could we even go simpler than this? And the answer is, we definitely could. I'm comfortable with this as an answer, but if you broke this as 3x cubed times x over 4y cubed, we can then replace the x cubed with a y squared, which turns us into 3x over 4y. Definitely a much simpler answer, but I'm going to argue well, this looks simpler. I guess maybe some algebra, simplicity we can work with on that. But as far as how do we direct students to do one versus the other. Very, very tough. On a free response, I would accept either one of those answers. On a multiple choice, it's going to be up to you to say, I know how to get from the answer I have to the answer that we're looking for down there. And then we get to logarithmic differentiation, which is my absolute favorite. So with this, we're going to say, if we have y equals 4 to the x, yes, I know that our derivative is 4 to the x, natural log of 4. We spent our last class talking about this. But logarithmic differentiation says we can take the natural log of both sides because the natural log is such a powerful tool. And when we do that, we can bring that exponent, properties of logarithms, exponent out in front. Be very, very careful though, we watch for domain. So watch for domain. Domain is such an important thing. Watch for it because we want to make sure that we're not violating any domain issues. Mainly when it comes to the algebra, we could work with it, look at the domain at the beginning, look at the domain at the end, and then see what happens as well. So when we take our derivative, 1 over y dy dx equals natural log of 4, and that's because natural log of 4 is a scalar. As a scalar, the derivative of scalar times x is just that scalar. Then we bring the y over to the other side and replace it with what y was at the very beginning. So that's the proof of why the derivative of 4 to the x is 4 to the x natural log of 4. And if you remember in class or when I said on my last notes, I tend to like to prove that with the logarithmic differentiation as opposed to proving it the other way because it's a little bit more natural. I am going to do like a little side note on here. That side note is, now that we've learned logarithmic differentiation, why haven't we used it before? Well, suppose we have y equals, say, x to the 4th. I could have said natural log of y equals 4 natural log of x, and I will always do this from here on out. I'll just bring that exponent in front. 1 over y dy dx equals 4 times 1 over x dx dx, which is 1. So dy dx equals 4 times 1 over x times y. And if I replace it as x to the 4th, I now get 4x to the 3rd. So could we have used implicit differentiation before? Absolutely. Or really the logarithmic differentiation. Such a powerful tool. It will work with everything that we've done in the past. It will work with most of the things we're going to do in the future. We just have to be careful of domain. Then why is this important? Because sometimes we have functions, and this is a function, but we have functions that cannot be evaluated without doing the logarithmic or cannot take the derivative without doing the logarithmic differentiation. So let's go ahead and start by taking the natural log of both sides. And then I am bringing that exponent out in front right from the very beginning. Hopefully you guys see that and are okay with that. And then from there, we say, okay, 1 over y dy dx. Now we have a product rule going on. And since we have a product rule going on, just have to be very, very careful with that. So with our product rule, v du plus u dv. And then, like before, we take our, we reduce, and then bring the y to the other side. Now then, I factored out the 3, replace the y with x to the 3x, and we should be golden. Now, one of the things that I do like to emphasize when I look back at this kind of problem, I say, okay, what kind of function was this? This is sort of like a power function. This is sort of like an exponential function, but it's not really either. However, the derivative of the power rule sort of shows up. If you notice, we have the 3x that we brought out in front. Now, unfortunately, with the nature of this one, that x that was right here reduced. I mean, that's kind of good, but that x reduced. So you don't really see that 3x brought out in front like a power rule. And also, you don't see that -1, which is where that came from. But we don't see any of that because it's sort of masked by this derivative. And try to do that. Oops, one more time. And it's not going to work. So now also, if we want to look at this as an exponential function, the natural log of the base has to be part of that derivative, which it is right here. So both natures and both changes of how those two functions work are built into the derivative. I talked through it. Hopefully you understood a little bit about that. but all the rates of changes should be shown in the derivative. For C, this is a perfect example of why we'd want to do some logarithmic differentiation as opposed to doing just like a power rule with an extended product rule. Now, could you do that? Absolutely. I chose to do this implicitly, logarithmically, and then break it apart term by term. So the upside is the derivatives tend to be much, much cleaner at the start. Downside is taking it to the overall solution ends up being a little bit more, I'll say annoying, but it's pick which operation you want to do first and go with it. Both are valid. I've had students who did in class, did them just straightforward. Some did it logarithmically. We both get the same answer. Example number 8, find the points on the graph which we have a horizontal and a vertical tangent. So I took the derivative, pretty straightforward derivative. Like before, brought the dx's to one, dy dx's to one side, everything else to the other side to figure out this expression. Now, horizontal tangents are when my numerator is equal to 0. And I did that. I get x minus 1 equals 0, so x equals 1. Kind of like I did in the other problems, substituted in to figure out what all of those y variables are. So we have horizontal tangents at these 2 points. And then we change the colors just so we can see a difference. Something that, we're just going to go green. So denominator, where that equals 0, gives me my vertical tangent, so y equals -2. Kind of like before, we worked our way through it to figure out the x coordinates where that's true. So I now know where my vertical tangents are. Does this make sense? If we took a look at this and said, wait a second, 4x squared plus y squared, this looks like it's an ellipse, and sure enough, this ends up being an ellipse. If I remember right, it is x minus 2 squared over 1 plus y plus 2 squared. That might be x minus 1 squared, and y plus 2 squared over 4 equals 1. We could see the horizontal and the vertical tangents. If I graph that, my center is at 1, -2. And then vertically, I go up 2 and down 2. Horizontally, I go right 1 and left 1. And so it makes sense why I have horizontal tangents at 1, 0 and 1, -4, which would be right here and right here. Go ahead, complete that ellipse. It's a very tiny ellipse. And then I have vertical tangents at 0, -2, right here, and 2, -2. Yay, it makes sense. I love when math makes sense. Moving on, we have derivatives of inverse functions. And if you remember what I said at the very, very beginning when I was talking about the implicit, that I said the inverse, or when we have an inverse function, when we take our derivative, we end up with a reciprocal slope. And that's going to show up in a lot of the stuff of what we're doing. Now, just a quick recap. If we have an inverse, we must have a one-to-one function for us to have an inverse. From a calculus perspective, as long as this is a continuous function, what happens is the slopes are either all positive or the slopes are all negative. It's terminology that we call monotonic. Very, very important terminology, monotonic. So that said, we could use calculus to determine if the function has an inverse. Now, this isn't a pure way for us to be able to do this. And I say it's not a pure way for us to be able to do this because, well, we could find ways of breaking this. But we take our derivative, set it equal to 0, and then we can test some values. It turns out that our slope's always positive. Therefore, we are able to have an inverse. On this one, found the derivative, set it equal to 0. Found some x values where that's true. If you remember, sine equals 1. Sine of x equals x. Sine of x looks like it's supposed to be -1. So I'm glad I caught that, which gives us 3 pi over 2 and 7 pi over 2, et cetera, et cetera. Turns out that really all of these are where, or all of these are going to be negative. Now we do go through a slope of 0, and that's okay. To go through a slope of 0 is we fine, but if you have an extended slope of 0, then it's not going to be monotonic. All right, derivative of the inverse function. We know that the points of inverse functions are going to be reflections over the line y equals x. And something that I'm going to do here that I did in class, I'm going to call this b comma a and this a comma b, just because it's a little bit more consistent with the notes that I have down at the bottom. I'm going to take this off. So a comma b, if a comma b is on a function's inverse, b comma a is on the function. Now, doesn't seem that important. Let's take a look at the meaning behind this. We know that we have y equals the square root of x and y equals x squared, two pretty well-known functions which are inverses of each other. So that's great. Now what we're going to do is say at the point 4, 2, our slope is going to be 1/4. You could do the math on that one. I promise it's true. At the inverse point, the slope is going to be the reciprocal. 9, 3 and 3, 9, inverse points, slopes are reciprocals of each other. So why do we care? Why do we care? Because sometimes when we have a function that looks like this function does have an inverse. We could prove it if we really want to. I don't really want to right now. But the question is, how do we find f inverse prime? F inverse prime, meaning the slope of the inverse function at x equals a. How do we find that? Well, let's find the inverse of this function, and we can try switch the x and the y, solve for y, until we realize I do not know how to solve a fifth degree polynomial function. So I'm kind of stuck. What do I do instead? Let's use this fact. This fact is f inverse prime of a is the reciprocal of f prime of b. Now, in order for us to do this, we need to recognize that the point a comma b is on f prime. That's what I was trying to show you up here. Let's call ab on f prime. If ab is on f prime, b comma a is on f. So if I want to find f inverse prime of a, I really need to know f prime of b. Well, how do I do that? A is going to be the y value on my original function because it's the x value on the inverse. So the y value equals this expression. Now I'll tell you, we have to intuitively come up with this answer. Intuitively come up with this answer, meaning test some values. On a problem like this, I would never give you something that's going to be really nasty for you to figure out. I promise the AP does not do that either. Usually the AP has the answer of 1, -1, 2, or -2. So something pretty straightforward that you can come up with. So x equals -1. So what are we going to do with that? We have to find f prime of -1 because that is the reciprocal 1 over f prime, f inverse prime. Yeah, let me just not write that. It'll be the reciprocal of the inverse prime of -2. So f prime of x, kind of a straightforward answer, f prime of x. And so 1 over f prime of -1 is 1/13. We could do the same thing here. So this time, I mean, I do recognize that we can't find the inverse cosine of y. We could do that, but then we have to know inverse cosine's derivative, which we're going to do in just a moment. So f inverse prime of 1/2 is 1 over f prime of some number. As we go through it, this one is pretty easy to find algebraically, that would be x to the 5 over 6. And so to find f inverse prime, we're trying to find f inverse prime of 1/2. That's equivalent to 1 over f prime of 5 over 6. So we find f prime of x, f prime of x, f prime of 5 over 6, and then reciprocate it. Which leads us to the inverse trig. When it comes to the derivatives of inverse trig, let's start off by saying, okay, let's go ahead and use inverse functions, sine of y equals u. And then the derivative of sine of y is cosine y dy dx equals 1 to the u dx. Great. How do I figure out what's going on? I don't know the cosine of y. I know the sine of y. Sine of y is u. So how do I figure out the cosine of y? Draw a triangle. Yay. I got excited about this, by the way. To draw a triangle, we know that y is the angle. Sine is opposite over hypotenuse. So the third side is square root of 1 minus 2 squared. Let me zoom out a little bit. I just want to spoil a surprise on that one. So to solve for dy dx, it's 1 over cosine, and 1 over cosine is that. We could also said secant y, that would have been okay So the derivatives of all three inverse trigs can be solved this way, or really proven this way. So arctangent, so tangent y is u, derivative of tangent is secant squared. Well, in order for us to figure out dy dx, that we need to now know cosine of y, which prompts us to say, let's draw the triangle. Tangent of y is opposite over adjacent. So to find cosine, we need to find our third side, and then we substitute that in and square it to get our derivative of tangent, arctangent. And then derivative of arcsecant. One of the things that I want to point out as we draw our triangle, we tend to draw our triangle in quadrant 1. And I'm going to erase this temporarily. We typically draw our triangle in quadrant 1, but the triangle doesn't necessarily have to be in quadrant 1. If this triangle were in quadrant 2, this would be a ratio of negative u over negative 1. So to fix that, we always make this the absolute value of u in quadrant 1. That way we don't have to worry about whether something's positive or something's negative. So like before, proving this, the derivative of secant is secant tangent. And then to solve for dy dx, we get cosine y, cotangent u, cosine y, cotangent y. So this is our cosine of y, this is our cotangent of y. Therefore, we have our derivative expressions. So this is something you can memorize if you wish. I prefer that you prove these, or at least work through the proof until you know these. The derivatives of the arc trig functions are something that in Calc BC we're going to be working with a lot more primarily second semester, especially when we do integration of inverse trig, as well as when we do trig substitutions. We have to know which of the three trig functions we want to work with. And I say the three trig functions because, yes, there are 6 trig, but if you look at these derivatives, the derivative of arc sine and the derivative of arc cosine are purely opposites of each other. Opposites of each other, opposites of each other. So when it comes to our derivatives being opposites, typically we could use either, or typically we're just going to be working with these 3 functions. Now I'm sure I'm going to throw a derivative of an arc cosine in there somewhere just for fun. So how do we work with it? Derivative of the arc sine of t squared, that didn't quite line up properly. 1 over the square root of 1 minus what's inside squared times the chain, which is 2t, to simplify to this expression. For part B, we have the overarching product rule going on, so v du plus u dv. And then really there's not a whole lot of simplifying that you can do here. You could write this as 1 plus x squared arctangent x plus x over 1 plus x squared. Not a whole lot. Mixing the trig in algebra, not the easiest thing. Then I have problem number C, or problem letter C. Problem letter C, once again, we have that same similar derivative. X arctangent of 2x this time, which means we have a chain of 2. Now the derivative would then be 1 over 4x squared. What I like about this problem is they'll throw a natural log in there. And if you notice, remember derivative of the natural log is 1 over what's inside times the chain of what's inside. If you notice, let's change color on this one. Not that. This whole expression and this whole expression are opposites of each other. Since these are opposites of each other, then we can simplify them we can cancel them out. We get our derivative as just the arctangent of 2x. Why is it special? Because I want to show that sometimes when we do our inverse of differentiation, which is integration, we can start off with an expression that has a really, really nasty antiderivative. Best way of saying it right now. 2 more problems. When it comes to D, something similar is going to occur here. We have this 1/2 on the outside, just to make life easier. So v du plus u dv. That's a really long derivative. And then the derivative of arc sine is this expression. Let's rewrite it and clean it up. 1 minus x squared to the 1/2. The 2's cancel, and we have subtraction x squared times that. And then let's write this to the negative 1/2 as well. We have 1 minus x squared as a common factor to all of them. We could write that to the negative 1/2, and we're left with these 3 terms, which those 3 terms can be rewritten as 2 times 1 minus x squared. And thus, we can get this overall, hey, this is the square root of 1 minus x squared. What that goes to show is, once again, that when we do antiderivatives, it's going to be a little bit nastier, but we can work with it. And the way that we prove that is with trig substitution. That's a special thing we get to learn in DT. Last but not least, I have this problem. A person's observing a rocket, and this is kind of like our prelude into 2.7, which is related rates. Theta is the angle of elevation of the rocket. S is the distance between the person and the rocket. My goal is to find an expression where theta is a function of S. So happily, I have this picture which shows the overall situation. I need theta in terms of S to begin with. So if theta is in terms of S, I have cosine of theta is 800 over S. Now, I'd like to do this one just applying the derivative. So theta is the inverse cosine of 800 over S. So our derivative is going to be -1 over the square root of 1 minus what's inside squared. So that what's inside squared is here, times the chain. The derivative of 800 over S is -800 over S squared. Yay. And then if we distribute the S squared to the denominator, we will get the square root 800 over the square root of S squared minus 800 squared, which is our overall expression. Thank you for tuning in. Hope this was very helpful to you, and I look forward to seeing you guys next time.